Mr. Eller will introduce our next group.
I'd like to introduce Chris Beren and Beren B Whitfield on their project.
Hello, I'm Chris Beren. My name is Beren Whitfield, and our senior project is over a wheel plating process. This is an overview of what we're going through in our project presentation. We're going to first go over the project scope. We're going to go about a little bit about the background of what we had to learn from the project. And then we're going to go into how we started to work on the project and understanding the system, and then understanding the movement, and understanding the process, and then go into our payback period. The project scope, local manufacturer of truck wheels is developing a new plating process that needs to be optimized, and it will analyze and optimize to check to see if the production process can make their stated goal. And part of it was to come up with recommendations to meet that stated goal if it wasn't met. This is some background knowledge about the product. The plating process is supposed to prevent corrosion. Currently, truck wheels are refinished every 3 to 5 years in the field. And with this new coating, they're trying to get to 8 to 10 years between refinishing. So the goal of it was to create a plating that created a wheel that fights corrosion and withstands the harsh environments that today's roads have, such things as road salt, rocks, debris, and sand. This is a little background about the plating process. Plating process adds a thin layer of metal material to a product, most commonly used for rust protection, decorative appeal, and friction reduction in some applications. These are some examples over here. These are some chrome-plated grills for pickup trucks. They require multiple cleansing rinses in between the plating, before the plating and after the plating. And this process was specifically an electroplating process that those using electric current to transfer the material through solutions and workpiece, which we will go into in the diagram on the next slide. In this diagram, we have the workpiece here in the middle, and we have the positively charged anodes over here to the right and left. The workpiece is charged negatively, and the metal ions are transferred from the anodes to the workpiece through the solution when an electric current is applied. Material handling of this process is handled with racks for the wheels. There are 6 wheels per rack. This is shown with the plant closed on this. There's 4 racks available for the system. This is shown with the plant open to access the wheels to change them out, reload them, or unload them in the process. Those racks are moved with overhead gantry trains. There are 6 overhead gantry trains, split 3 to each side. They look similar to this. These gantry trains pick up the racks with these 2 pins right here. So there's 2 pins so they do not rock back and forth when they're being moved horizontally. This is the AutoCAD drawing of the process layout as it is now. Each one of these is a tank. Not all of them are used for this process. It was before this a dormant bumper plating line that they're repurposing for this process. This is the production process in motion. These right here are showing where each crane is and what section, what tanks that they move the parts through. It changes colors as it's switched off between crane and crane, and it is turned opaque when it gets into the tank. As you can see, the tanks that are used are highlighted in yellow. Once it gets here to crane 4, there's a shuttle right here that takes it over to the 4 plating tanks right here. There's 4 in case they're for accommodate all of the racks to go. And then it moves on further on. There are 2 curing tanks that you can choose from, and it can go with either one of those, whichever one is open at that time. So the important thing to mention there is it's 2 separate sides of the plating operation. So there's what I would call the pre-rinse area over here on the right, which is connected by the shuttle, and then it goes into the plating operation here, which I guess the reason for the multiple plating tanks is how long it actually takes to do the plating operation and the curing operation. Those were potential bottleneck areas, so they were additional tanks were added at that point. So as you can kind of see, it goes out of the system, is taken out of the system at this moment as well. background of production goal. Production goal was 48,000 wheels per year being plated. Production shifts where there's 4 10-hour shifts per week, and with 50 weeks being worked per year, there'd be 200 shifts where wheels would be plated. To get to the 48,000 wheels per year needed for this goal with the 200 shifts, you would need to do 40 racks per shift and have a rack processing time of 15 minutes per rack. This plan of attack we used for this project, we first went through understanding the system, and by that we went focused on the time limitations of project, such as like the curing and the curing and the plating operations. This helped us fully define the system whenever we had all the times for all the different operations, for instance, plating, etc. We then went to understanding the workpiece movement. We wanted to focus on the crane movement itself, which trains move what racks when they move them. We had to also understand the crane travel limitations, what sections the cranes could actually work. And then lastly, we had to understand the process. So we focused on the total time, the process time for multiple workpieces for the whole 4 rack batch to go through the system. We took this production rate that we calculated from this and then compared it to the overall goal later on. First part of understanding the system was that we had to find the time critical steps. The main time critical steps were the plating at 35 minutes and the curing at 10 minutes. Those were the 2 longest process times that we had. Using this information and using all the other steps, time that we had, we were able to come up with a process flow map for the operation. And this will be shown on the next slide. This was laid out in the same way that is laid out physically in the plant, with the loading of work pieces coming in on this side, and each tank is numbered with corresponding numbers from the AutoCAD drawing, with the process time for each tank in this column, and the description of what each tank is doing. And we have each one of the time critical steps highlighted in red, and there are 5 of them. And after this, the biggest part of it, the unknown at this point, was the movements that the cranes make. We had to figure out how fast these cranes move, which tanks they move parts from, when they had to move backwards to pick up another rack going through the system. And we wanted to understand what the movement time for the cranes would be.
So as Chris mentioned, we knew what the tanks were capable of, what their process time was. But what we didn't quite understand yet was the actual travel time between each tank that the cranes would require. This was done through some time studies, as well as adding on to the Excel spreadsheet that you saw from earlier, adding the colors there, the crane limitations, where each crane can go, and what zone, what range. The limitations of the crane we didn't find to be very significant. Most cranes could go throughout most of each process on either side of the process. So to understand the movement of the actual cranes, we had to do time studies. So we went down to the facility and did manual time studies. The biggest graph there is an example of that. This is an example of a vertical time study. As you can see there, the up and down times are averaged, as well as give you an average up and down time. This was done with the carrier to symbolize how the cranes would react with actual product on them. From the horizontal time studies, we were also able to, at your bottom left there, come up with a velocity of about 18 inches per second for each crane, and also the shuttle speed of about 2.5 inches per second. So what all that meant is we were able to understand the travel times for each. So this is 5 examples of the 26 total travels that are within the system. For instance, if you look at T0 there, we took the distance from the AutoCAD file, used the average times that we found in our time setters for up and down, and then used the distance and the velocities for our forward. We also added a buffer for safety precautions and the realization that we were doing an ideal study for an unideal system. So bringing that all together, you have a Excel spreadsheet that looks like that was built up upon from the very beginning steps. But what that all means is we were able to understand that one rack can go through the system in a total time of 94 minutes. What you can break that down into a couple of different ways. Value-added time to the customer, which is only about 40 minutes of that, which would be the plating operation and a coating operation after that. As far as the necessary non-value-added time, that would be both rinses pre and post of the plating, which are required but not necessarily, in the customer standpoint, aren't effective. The non-value-added time, just regular non-value-added time, would be the movements that the cranes actually took. So now that we've understood how we can go through the system with one rack, what we still don't know is how quickly we could remove the maximum amount of 4 racks that we were given in this study through the system. Part of that is understanding the process itself from that standpoint, and then also the cranes optimization. For understanding the process, we use a tool called Yamazumi chart, which is actually a lean manufacturing tool used in a lot of different systems, most notably the Toyota way. Essentially, Yamazumi is a Japanese word that means to stack up. So essentially that's what it is exactly, a stacked bar chart that shows the workload and how it is spread throughout the system. For instance, in our example here, you've got 4 operators, and it's showing the different processes that each operator does and how that affects the overall process. Moving on to something that relates to our project, this was the initial Yamazumi chart done based off of the 94-minute one rack system. I won't spend a whole lot of time on this one, but the pie charts at the bottom show the breakup in between the necessary non-value-added, value-added, and the green, which would be the value-added time. As you can see, well, you can't really read it, but the orange graph, the orange part in the middle there, is the plating operation. So we realize that that's going to be a big part of it. Now, what this doesn't take into effect is that there were 4 actual plating tanks. Moving on to the next slide, you get a better example of what's actually happening in the previous graph and the graph after this. Each movement and each travel time and each actual tank process is stacked up to under which crane actually takes is moving that part. Moving on to the next one. This one actually is a little bit better representation of how the workload is spread out throughout the process, because it takes in account that you have 4 multiple plating tanks that can do the same thing, and 2 curing tanks that we mentioned in our animation that can also do the same process simultaneously. Moving on. So what that doesn't really show you, though, or what doesn't really tell you, is that, well, how much we can produce. So in order to do that, in order to understand how quickly we can put 4 racks through the system, we did a very big graph, a very big Excel spreadsheet on the right that you can see there. Zooming in on that to the left, you see that each crane movement is taken account for. So it was focused on crane optimization. So you wouldn't have one crane waiting for a part or for a rack to get done. It could go do other things while one rack was being processed in the tank. So to optimize, we created this to optimize the cranes in the plating process. And then what all this really means in this page, if you move to the next one, comes down to this here. On your far left, you see rack 1 total time in minutes, 98 minutes, came out right at 98 minutes. And then rack 2, 71 minutes after that, came out of the process, and then 24 minutes after that, and 26 minutes after that, 3 and 4. What that means is you had a total rack processing time for 4 racks of 221 minutes, which, if you divide it by 4, is an average cycle time of 55 minutes per rack. So we knew at this point we knew how quick we could go through the system, and we also realized that we had 600 minutes or 10 hours in a day. So with 221 minutes, you've got quite a substantial amount left. You should be able to do another rack. Well, what that actually includes is you can see another batch. that includes is doing an unloading and reloading, which will take 15 minutes for each, which brings you down to 341 minutes for the second batch of 4 to go through the system. This gives you a total cycle time for two batches to go through the system of 562 minutes, right below the 600-minute mark, so people can go home at the end of the day, and a cycle time per rack of about 70 minutes. Bringing all that into something to compare to our actual overall goal, on your left you see a brief study using the 55-minute cycle times per rack, basically not taking into account for any of the loading and unloading that has to be done, which would give you about 13,000 wheels per year. And if you would compare that to what the actual number of 70 minutes per rack that we configured with the loading and unloading of each of a rack system, you get about 10,240 wheels per year. Let's take a step back from this a little bit and look at our labor costs and a little bit of our payback period. For our students and USI faculty labor, we got about 240 hours together, $15 per hour for us, which is about $3,240, and about $2,000 worth of USI faculty help. As far as the only for this process, the only thing that was in our scope of the presentation was the cost of the racks themselves, which were $20,000 a piece from our client, and with 4 racks, you got $80,000. How would you get your money back on that? As far as the payback period, it's estimated that the total cost of manufacturing was $75, and that we'd be able to sell the wheel for $100, which gives you an estimated profit of $25. Now, if you sold every single wheel you were able to produce that year, you would get a profit of $256,000 and a payback of about 114 days, 4 months for the wheel. So, in conclusion, with only 4 racks in the system, you are capable of 10,240 wheels compared to the 48,000 wheel ultimate goal. Now, what that means is essentially at this point you're going to need a lot more racks, right? Well, if you move on to the next slide, we did a brief analysis of how many more racks we could do. So at that point, we said, what if you could do? What if you had another 8 racks that were ready to go halfway through the system halfway through the first batch is processed?
Basically, when the first batch is all the way into the plating tank, you add in the second batch of 4 racks, you start it through the system.
Yeah. Based on our previous analysis of the crane optimization movements. So what that allows you to do is get 3 total batches of 4, so 12 racks through the system in one day, increasing your ultimate output to about 14,400 wheels per year. From that point on, you're going to have to look at, in our findings, you have to look at the cranes, the drawbacks of the cranes, for one, and upgrading or adding more cranes to increase your output. Also, another recommendation that we have would be to use a software program such as Arena to do modeling of this simulation and model of this process to understand its full capability.
We just want to acknowledge everyone's engineering department that has helped us out, and we'd really especially like to acknowledge Mr. Dave Elliott for helping us out this semester, and Dr. Tom Downs, I don't see here, and Dr. Marco Garcia, and then Donna especially. Without her, we wouldn't have made all the deadlines and got everything done. And you have any questions?
Questions?
I'll ask a question. I guess not having seen your spreadsheet, there's a part that's unclear to me. How come you couldn't have started batch 2? How come after 90 minutes, you start the whole thing, 90 minutes later the first rack comes out? How come you can't unload that, load it on, and set that one going while you're waiting on 2, 3, and 4? What? Do you see what I'm saying? Because you have the unloading time once all four racks are out. Why not keep it going?
I mean, essentially you could, but either way you wouldn't, you'd still only get 2 batches in that processing time as far as the 2 or 8 racks total to the system. We looked at that actually, and once we created that, yeah.
Okay. And kind of a related question, but maybe not. The limitation, you say that the cranes are a limitation. It seems to me like the process itself is kind of a limitation. Do you need more than 4 tanks of the coating and more than 2 of the curing? Would that be a better add? Because once you get racked, the cranes can't jump over each other, so you gotta worry more about the direction. If you had different things, you could drop them in and leave them for 40 minutes. Would that be a better solution?
Not necessarily. Reason being I guess there's a couple different ways I can answer that question, but what it comes down to, I guess, is we looked at it a little bit from a different perspective as well, kind of halfway through this, which is actually in our paper, but we didn't show here for time reasons. But you could, if you essentially divided the 35-minute time by 4, you could load one essentially every, what was it, 8.75 minutes, something like that. But what that doesn't account for the cranes at all. But if you consider that, just loading that the 8.75 minutes for X amount of time, you can get a lot through. But I can't remember what our numbers were, but we found that the rack numbers were seemed somewhat astronomical. How many racks you would actually need to keep the system flowing?
I see. So if you add more tanks, you have to add more racks, and they're not.
Right. Yeah.
Would you please elaborate on the cranes? Do you think that the cranes are a limiting factor in the system?
Yeah, the way they are right now, there is a lot of, like, when they're trading off between the racks, they have to travel back while another one's sitting up here in another tank, then they have to bring that one up and then move that other one forward that's up here. With those movement times of having to travel back by multiple tanks, in like one case, I think they had to travel back over 4 tanks to get to the next tank that was actually used. If the cranes can move faster, which we know that the crane speed could be faster, that never was tested with them going faster, but if we sped the cranes up, that could help some with that situation. Do you have anything to add to that?
Another part, I guess, in the previous slide where I showed the Excel spreadsheet, you couldn't really read because it was so astronomically huge. It's hard. Within that, if you start analyzing it the way we had to create that spreadsheet, you realize that the cranes were always moving. At times, they had to leave. In some of the non-time critical steps, they had to leave a rack in there for longer than the recommended time, just because there were times where where the crane had to do something else for a time critical step and you couldn't do that together. That might actually help you get through
That's kind of answer the question.
Chris?
How close is this to being implemented?
We're at least 2 years out for the client. There's a lot of like currently it's a dorm. It is a dorm system. It's not actually being used for anything right now. It's being set up. So there's a lot of stuff that has to be into that. The SolidWorks files that we showed for the racks are designs that are being fabricated currently. So we don't actually have any data as far as with an actual rack either. So it's at least 2 years out, if not.
Is the shuttle a bottleneck?
We didn't find it to be as much, no, because the kind of going back to the opportunity charts, the shuttle itself is between crane 6 and 3, so we didn't have any problem getting the racks over from 6 to 3. It was once they got to the zone that crane 3 covers, which is the plating operation, that we had a lot of issues.
Thank you.
Any other questions? Let's give it a hand.